All right, so nuclear stability. What evidence do we have that mass and energy are equivalent? Well, what we see is that in any nuclear reaction, a tiny amount of mass is lost. And an energy corresponding to that loss in mass is gained. Going into that, the energy to mass conversion is E equals mc squared. If I make this much mass disappeared, I get this much energy. So, sticking with Einstein and his weird relativity, why is it impossible to accelerate an object to the speed of light? Because it would require an infinite amount of energy to move that fast. As we get closer and closer to the speed of light, what we actually see is that the mass of the object increases. So the faster and faster and faster and faster and faster we go, the more and more and more and more and more massive our object gets, which means it takes more and more and more and more and more energy to make it go faster. So the energy that we're putting into our mass is going actually into two different places, because things get weird when we go so fast. Some of the energy we're putting in is going into speeding us up, but some of the energy that we're putting in is actually being turned back into mass and making this thing more massive. So to get up to the speed of light actually would require the object to have infinite mass, and so it would be infinite energy to get that fast. That's why we don't do it. How much energy, according to Einstein, how much energy could be released from 0.02 kilograms of matter? Well, E is equal to mc squared, so that energy is going to be 0.02 kilograms times the speed of light, 3 times 10 to the 8th meters per second squared. That means that energy comes out to 1.8 times 10 to the 15th joules. That's a ridiculous amount of energy. How much matter would be needed to create 1 times 10 to the 8th joules of energy? We're going to take that equation and we're going to solve it for mass. So it's just the energy over c squared. So we're going to have 1.1 times 10, to the 8th joules divided by 3 times 10 to the 8th squared. So when we do that, we get 1.11 times 10 to the negative 9th kilograms, which is not very much mass at all. Why do atomic nuclei undergo radioactive decay, fission, and fusion? In short, the nucleus is relaxing or seeking a more stable state. To say it a bit longer, all right, so radioactive decay, you just have something that's big. It has a whole lot of neutrons, has a whole lot of protons inside of the nucleus. And it's so big that the repulsive electric force and the attractive strong force are fighting with each other. And every now and then, strong force loses and the thing breaks apart. That's decay. Fission, what we do is we take something that's close to being unstable and we add a neutron to it. It just messes the whole thing up and it breaks apart. Decay and fission look a lot alike, but decay is a random, naturally occurring process. Fission is something that we drive to happen by adding things to the molecule. In fusion, what happens is because of, we see this mostly in stars, because of the massive amount of heat and the massive amount of pressure that these things are undergoing, I'm putting nucleuses really, really, really close to each other. And it turns out that two hydrogen nucleuses would rather just be one helium nucleus when we jam them together. That's a more stable state, and so they slide into that. That's fusion. So, okay, so looking at each of these things, what you need to do is consult a periodic table. And you need to see if the element is heavier or lighter than iron, essentially. If it is lighter than iron, like helium, you're going to have fusion. And magnesium is lighter than iron, so you're going to have fusion. Lead is heavier than iron, so it's more likely to undergo fission. Platinum, heavier than iron, more likely to undergo fission. Iron is very stable, so nothing's going to happen. Carbon, lighter than iron, lower number on the periodic table, fuses. Selenium, heavier than iron, fizzes. It's going to break apart. So the idea here is this little graph. And it's got atomic number down here. And then it has mass of nucleon. What basically this means is the mass of protons and neutrons. And what we see with this is a graph that looks like this. We have iron right here. This is a stable spot. What this tells us is that the mass of protons and neutrons changes in different elements. It's a crazy thing. What that means in hydrogen, way up here, hydrogen and helium, the mass per nucleon is bigger than it is for iron. So the mass of a proton in hydrogen is more than the mass of a proton in iron. And so when you take a bunch of random protons and stick them together to make an element, so mass of hydrogen, mass of helium, when you put these together, they get lighter. And when that happens, it releases energy. So by combining masses, by getting more and more atomic protons in the nucleus, we're going to release energy by doing that. Over here, we're going to release energy by splitting things apart. When we go from this to two smaller elements, we get less mass overall because the actual mass of the protons and neutrons gets smaller. That's what accounts for this E equals mc squared energy. This is a very cool thing, that the mass of protons and neutrons changes when you go to different elements. Iron's down here at this stable part. That's why nothing happens. The things that fuse are over here, where a higher atomic number gives me less mass per nucleon. And we're going to, sorry about that. And we're going to fizz when we're over here, when a higher atomic number gives me more mass per nucleon.